So last time we were talking about how you can specify a Markov random field, an undirected probabilistic graphical model. And I was not quite finished with giving all the ingredients of such a specification. So this is what I want to start with today. And afterwards, I want to tell you how you can do energy minimization in such Markov random fields. And we will discuss that energy minimization in terms of a standard optimization problem, an interlinear programming problem. So the good news is that this allows you to formally, write down, and if you have a big enough computer, solve every discrete Markov random field in the world. The downside is that actually you will need a bigger computer than anybody has for many models, which is why we will talk about other formulations or approximations in the next few weeks. But it is nice to know that at least for small models, you can find a formulation which you can simply put into a solver, and you will know that you can get the exact answer out. Okay, so in terms of models, I mentioned this tracking by assignment. Here we had the detection random variables shown in blue. In black, we had assignment random variables shown in red, and then a lot of factors, some unary factors shown in black and red, these squares, which tell us if we believe that there is actually a detection in the data, or that there is actually an assignment, and the deterministic conservation laws that were saying that we should not lose any cells in the process, or we don't want spontaneous appearance of cells. I presented this as an example of a very irregularly structured graphical model, and then I gave you 3 more examples. So grab cut, where we have 0, 1 labels for our nodes, foreground or background. Stereo, where we have a couple of labels, like are we in depth zone 1, 2, 3, or 4. And finally image denoising, where I argued we could use continuous domain random variables. But all these graphical models had the same simple graph that you see here. So there are 2 ways of looking at this. We can either say that these graphs are not very expressive because they leave us so much room for interpretation, or you can argue the other way around, that this is a very powerful model, that with such a generic structure you can encapsulate such different computations. Okay, and we were starting to say that to specify a Markov random field, what we need is we need to say what set of random variables we have. And secondly, we said that we want to have a graph or factor graph, 2 examples of which you can see here. So we have the set of random variables, we have a graph or a factor graph, and this factor graph only selects a family of distribution. So for example, let's say I have some prior distribution concerning of 2 isolated random variables. And I want to show you a few pictures, so as opposed to 2 variables which are coupled by a factor. So for example, I'm now showing you a couple of bivariate distributions. For example, this one here, I'm drawing isocontour lines of a Gaussian. this would be an example of a distribution which I can model in terms of two independent variables. Yeah? So one of them will have a Gaussian distribution, and the other one will have a Gaussian distribution, and then the joint distribution is an uncorrelated Gaussian. So that would be an example. Whereas if you want a bivariate distribution looking like this is also a Gaussian, but here we have some correlation between the random variables. Yeah? So they are no longer independent. So this would be an example of a bivariate distribution that can only be modeled by such coupled random variables as we see on the right. Now, how about this distribution here? It has 4 bumps. Can I represent it in terms of independent random variables? Yes, why?
Yeah, because it's completely symmetric, and I can find a point in the middle where I can plug also in, if I want to take it two-dimensional, say an axis where everything is more or less symmetric.
Yeah, so you argued by symmetry. Does anybody remember in more general terms what is the characteristic of two random variables being independent? What's the statistical definition of having independence of random variables? Yeah?
Covariance is
No?
the joint distribution factorizes.
Yeah. So we can find two univariate distributions. For example, one which looks like this, and one which looks like that. So, excuse me, I'm now switching. In the middle, I have a representation in terms of isocontours, and on the sides, I'm now arguing in terms of densities. But this is a one-dimensional distribution with some density p, and this is a, excuse me, one-dimensional distribution with some density p. And if we take the product of these, then we get pretty much the thing in the middle. Yeah? How about this guy here? Independent or not? No, exactly. Okay. How about this? Trying to draw a checkerboard pattern now. Independent or not? Independent. Somebody has another opinion? Yeah. So I claim it's not independent because if I look at the marginal distributions here, I'm getting a histogram. So I have 2 units of density here, 1 unit of density there, 2 units of density here. So this is my probability density. Let's do the same game here. 2 units, 1 unit, 2 units. And if we now take the product of these two, I would also obtain some density in the regions which here I have marked, where I'm now writing the 0, where supposedly there should not be any density. Okay, so this is an example of, again, something that can only be represented like this. But on the other hand, if on the other hand we have the following, density here and here and here and here, but not in the middle. Now you're right. This would be independent, and indeed, it's the same situation as in the previous picture. Huh? Okay, and somebody earlier said independence is given whenever we have zero covariance. This is true only for the Gaussian, for the multivariate Gaussian. Well, yeah, okay. Here, I always use the same distribution in the horizontal or the same type of distribution in the horizontal and vertical direction. But we could, of course, have a random variable which is continuous in the one domain and discrete in the other. So we could have, for example, let's say if we multiply a Dirac density, let's say a trivariate Dirac, with a Gaussian, then the result would be, this is a bit hard for me to draw now, but we would have trying to indicate this now with the thickness of this line. We would get such a stripe pattern here. So we have three Gaussian densities. This again can be written in terms of independent random variables. Okay, if I zoom out a little, I could continue and invent many more on either side. This is what I want to stress when I say that each factor graph represents a whole family of distributions. So the two that I showed here, they can represent all the ones that you see below, plus many others. And the factor graph that I've been showing here can encode all distributions that you see below, plus many, many others. Okay, so now if we want to talk about a particular distribution, then we want to say which member of the family are we talking about. So what I need to specify in addition is the domain of the random variables. And when we talk about the domain, let's revisit our examples. We had the tracking by assignment example, where I had the detection variables, and in the, let's say in the simplified model, these would be binary, and we have assignment variables, which in the simplified tracking model would also be binary. Then I mentioned the grab cut algorithm for interactive segmentation. Here we have a foreground background. So this can be encoded as 0, 1 in stereo. Here I have to make a choice if I want to encode the depth in terms of a discrete or in terms of a continuous random variable, and depending on what choice you make, it will take you down one or another avenue of image processing research. Yeah? These are sometimes people which unfortunately don't talk to each other as much as they could. In many cases, so it's been quite popular to use discrete random variables here. So to say the depth is 1, 2, 3, up to some maximum depth level D. But this is of course arbitrary. You could also model this continuously. And then I mentioned denoising, where we had the intensity. And in the model that I have shown briefly and that we will talk about more, we will say that this is a real number. Actually, this is nonsense because we cannot have negative intensity, so I should put just the non-negative numbers, but in practice people often model this with just really real numbers. Any question?
So just one short question. So what's the difference between the domain of the RVs and the sort of the RV? So what is there more to a random variable with its domain?
You are,
I'm referring to the first point.
Okay. So you ask what is, when I say what is the set of random variables versus what is the domain of the random variables. There is, so I was wondering if I should have merged set of random variables with the graph, because the graph consists of vertices and edges. I left it as an extra point because it alludes to this modeling decision of what are your entities. So
it's also because I read sort, but it's set. So
it's a set of random variable.
Yeah.
So you know, what is your fundamental entity? Is it a pixel, or is it a superpixel, or is it an object? Yeah? I can make this. Okay. Let's say the domain of random variables. I could also say that I want to mention or specify the distribution of these random variables, but actually the distribution, I will encode this in the factor. Yeah. So when I say that I have a random variable with a given domain, then the factor, if I have a unary factor, will tell me, let's say if this is, assuming that this is a real, that this random variable takes values on the real line, then it is the nature of the factor which would tell me, is it a Gaussian or a Laplacian, or what kind of random variable is it? Okay, so lastly, we need the potentials or the factors. So when I'm saying factor, I'm more talking about the representation where I multiply probabilities. If I'm writing potentials, this perhaps means or alludes to the fact that I'm here arguing in the energy representation. So after taking the negative logarithm. Okay, so the unary potentials determine the distribution of a random variable, as I've just argued, and then pairwise or higher order potentials. So by higher order, I mean factors that involve triplets of random variables or even more random variables, pairwise and higher order potentials. They determine the interaction of random variables. And here I want to distinguish two cases. We have what is sometimes called a pure Markov random field, where, let's say, a pairwise potential does not depend on the data at all. So the pairwise potential does not depend on the observations. And I'm going to make a more detailed picture this time of a standard Cartesian MRF. So I'm showing a couple of more random variables than we previously had, because previously I omitted the observations. Yeah? So let's say these are the latent random variables. This is the random variables whose state we want to estimate, and these are our observations. And in this graphical model language, the observations are often shaded, meaning, let's say if this is a stereo problem, then I have, or let's say if this is a denoising problem, then these shaded nodes would represent the intensity that I have actually observed, and the unshaded nodes would be the presumed true intensity that I want to estimate. So these are, for example, the observed noisy intensities, and this here are, for example, the true colors of different pixels. And these unary potentials here, they are often called the likelihoods. So they couple, if I only look at an observation and its latent random variable, they couple my estimate to this observation. And if I did not have all these pairwise potentials that I'm here coloring in blue, if I did not have the pairwise potentials, then I would simply use the observation as my best estimate. But now I have these pairwise terms that allow me, for example, to bring in a smoothness assumption. And I'm now talking about these pairwise potentials here. For example, I can say that this psi ij of xi and xj, these are the random variables, xi and xj. And now I'm using capital I for the indicator function. So this gives me a penalty of +1 for every label transition, or a penalty of 0 if there is no label transition. And if I have just two possible labels, then this is the Ising model. Or if I have more than two possible states, then this is the Potts model. But also last time, I discussed a different kind of potential, namely one that could also depend on observations. And so now this was the pure MRF, and I could now also let my potential depend on the observations. For example, I could say psi ij depends on xi and on xj, but also on observation oi and on observation oj. And the example I gave the last time was the following. We used again the indicator function, but now this is multiplied with the following term. And the effect of this is that if my image intensities are very similar, then I'm going to pay the full penalty. So if I have a label transition where there is no indication in my image that actually something is changing, then I have to pay a big penalty for this label change. But if there's anyway an edge or some other indication of something going on in the image, then I only ask for a small penalty for this label transition. And in this particular case here, this penalty decays exponentially with the magnitude of the local gradient in the image. Now, in the graphical model, I now need to express that so the blue potential or the blue factor, it only depended on two random variables, so hence it was a pairwise factor, and I only had to connect it to its two neighboring random variables. But now I have this function which is an argument of 4 variables. So I need to augment my graph here by saying, actually there's a connection also to these observations here. And this is called a conditional random field. In which the pairwise and the higher order potentials can depend on the observations. And there is a bit of a theoretical Überbau to all that, because in a conditional random field, overall I model only the probability of my latent variables given the observations, and hence these models do not allow me to sample the latent variables and the observations jointly. Yeah? Whereas these pure MRFs, they can model both the latent variables and the observations. Yeah, so note up here I write a comma, so I can model the distribution of my unknown, my latent random variables and the observations. And down here I don't have a comma, but I have a vertical bar, meaning I condition on my observations. And these conditional random fields, they comprise the ordinary Markov random fields. So on the one hand, they're more limited because I cannot sample from them. But on the other hand, they comprise the ordinary Markov random fields as a special case. So in that sense, they can be more powerful, and they are indeed often used in natural speech processing and also in image analysis. Okay, and overall, let me say the motto, if I may say so, of Markov random field modeling is I'm making this up. Yeah, this is not a technical term here. Let's say you can specify locally, and this shall sound a little bit like a political slogan. Act globally. So the idea is that you specify only local interactions, but because you can propagate information through such local interactions, you can actually obtain global models. And formally, it would be allowed to specify things not only locally. Yeah. So, for example, I could have a random variable which I connect to all other random variables. Let's say, literally to all random variables. I could have that. Formally, this would still be a Markov random field, but it would be very non-sparse. Yeah? So I would have here connections between everybody and everybody, and Markov random fields. So the power of these methods is that you try to be very sparing or sparse in your specification. You try to model only an absolute minimum of interactions, and these interactions should usually be defined locally. And this is both to simplify the model specification, but also in particular to model inference, because it turns out that so essentially the more loops you put into your graph, the harder the inference problem becomes. Okay, now I've used this word a couple of times, inference. What does it mean? It is often translated colloquially as reasoning, so a reasoning about data here. For example, if we have given some observations and we have given some model, then I can ask for the set of latent variables or the interpretation, or I can ask for the configuration that will give me the greatest posterior probability. And this is the map problem. So map or maximum a posteriori problem is to find that configuration that has the greatest likelihood given my observations. And this act of finding x hat, if we use this energy picture, then we would call this an optimization problem or an energy minimization problem, or you can also call this inference. So if we want to use Markov random fields, this generally encompasses three phases. There is a modeling stage where we say, what is an object? What entities do we describe with a random variable and with what kind of random variable? What kind of interactions do we need to specify? Then secondly, there is the parameterization. And thirdly, there is inference, because we want to find out about either the most likely configuration, or we want to estimate the distribution of, we want to find a posterior distribution, let's say, of latent variables given our observations. And there are now a couple of arrows that I should draw. One is that this parameterization we can of course do by manually tweaking parameters until we like the results, but this is generally tedious and often impossible to do well if you have many parameters in your model. And what do I mean by parameters? Last time we saw that we had these factors. I showed these truth tables somewhere, yeah, like having these numbers here, 0.99 or 0.01. I argued that we want to somehow estimate these numbers from or in relation to local observations. So in that sense, I specified a conditional random field. So we need to find these elements of our tables that describe our factors. And ideally, we want to learn these from training data. And if we want to learn these from training data, then we have a loop where we start with some parameters, we do optimization, we look at the result, perhaps we can even compute a derivative of sorts, and then we go back and update our parameters, and then we repeat this until we have nice results, at least on our training data. So I've put parameterization before inference, but really we need to establish the inference procedure first before we can do learning. And then secondly, you could either start, so usually what you would do is you would start with the simplest possible model with either no interactions or just the fewest interactions that you absolutely need. Then you look at the result, and if you're unhappy, then you need to make your model more complicated. Yeah, so for example, in stereo estimation, the first thing you would do is just try to use these local correspondences to estimate the proper depth in a given pixel. And if this is good enough, then why would you do anything else? But when it turns out that no, this is not good enough, then perhaps you want to introduce a smoothness prior. Yeah? So after having done inference, and if you don't like the result, then you can reason about how you should make your model more more complicated or more expressive. And the modeling, in turn, you always try to keep things tractable. So it depends on what inference procedure you have available, and which inference procedure you pick depends on the model you have chosen. So in real life, usually, if you solve a complicated problem, you don't just write down your final graphical model and then optimize it, train the parameters, and you're done. But this is typically an iterative procedure, which I'm trying to indicate here with these arrows. Okay, so this is formally how you specify a Markov random field in a few steps. And then depending on these choices you make, you can end up with, these examples we've discussed. You can end up with a tracking by assignment model, or a grab cut, or a stereo, or an image denoising method.